Hey folks, welcome to the second video in 8.1. This one's on pressure. This is something that you also study in your chemistry class. We're going to go into a little bit more detail about where pressure comes from and things having to do with depth of fluid and that sort of thing. So pressure is defined by the equation force perpendicular divided by the area. So I'll spend a little bit of time explaining that, but let me just fill out the rest of the information on pressure. Pressure has the units of newtons per square meter because it's force divided by area. That is given a name. The name of that is the Pascal, and that's abbreviated capital P lowercase a. It's a rare unit in this course anyway that has two letters instead of one. Pressure is a scalar. And now the SI unit for pressure is the Pascal, but in your experience, either in everyday life or in your chemistry class, there are many other units of pressure: pounds per square inch, atmospheres, torricellis, millimeters of mercury. The list actually goes on. But we're going to use pascals and kilopascals once in a while because that's the official SI unit. So this force per area. So the example I would give in my chemistry teaching days would be like you are walking along a frozen pond when the ice starts to crack, and how should you respond to not fall through the ice? So you exert a force that on average is equal to your own weight on the ice itself. The area over which you press down on the ice is equal to the area of the bottom of your shoes, or if you're ice skating, the bottom of your skates. So if you're skating across the pond, the pressure that you're applying is even greater because you're applying it over two thin blades instead of your entire foot. So let's say that you're walking on regular shoes, producing a force over some area, and you're exerting some pressure on the ice, and all of a sudden the ice starts to crack. That ice is starting to crack because the pressure underneath your feet on the ice is too great for that pressure for that ice to stay in one piece. So the way that you would respond if you didn't want to further crack the ice is you just lie down on your belly. Because you are not able to change your own weight just by reorienting yourself. But if you lie down on your belly, now the area over which that force is applied is the entire front of your body. So your torso, your legs, and if your arms are on the ice as well, then your arms are dividing that or increasing that area. So you are able to decrease the pressure by which you are applying to the ice by increasing the surface area that your body is in contact with the ice. Now, for fluids, we'll do a little bit with P equals F over A in some other problems, but for the most part, we focus on fluids, and fluids being liquids and solids, they exert pressure in every direction due to their own random particle motion, and so if they're in a container, they're exerting pressure in every direction on the walls of that container. And so, atmospheric pressure is a result of that. As you walk around in your daily life, you are walking around at the bottom of a column of air. And that column of air is pushing on all parts of your body, but in general, it's mostly pushing down on you because there's so much air above you, like 60 miles worth of air above you. So the atmospheric pressure on most days is around, or on all days really, is around 100,000 pascals, which is about 100 kilopascals. Now, if you took AP Chemistry, then you might be like, you're rounding, it's 101.325 kilopascals, but we're going to be using 100,000 because that is close enough to get a good understanding. So that's the pressure that you've been living with your entire life, the air above you pushing down on you, and you don't feel it because you've been feeling it your whole life. In PSI, that is 14.7. Which we might use as just a reference from here or there. So that pressure is always there on everything that is in contact with the atmosphere. As we start to descend within a fluid, the pressure will also change. So here I have a vat of, let's say, water. The atmospheric pressure exists on the surface of the water, so it's like pushing down on the top of the water at all times. But then as you get into the water, the pressure will continue to change. Now, points A and B are on different sides of the vat. They're a distance little h underneath the surface. Point C is right in the middle, and it's a distance big H from the top. There are three factors that influence the pressure from a fluid depending on the properties of that fluid. So the fluid density is a factor that affects pressure. In fact, the pressure due to a fluid is proportional to the density. The more dense that fluid is, the more it can collide with you, the more particles can collide with you per moment. And then also, if you are submerged in the fluid, the more pressure there is coming from the particles above. The next thing that influences pressure is the gravitational field strength. And that's little g. And again, pressure is proportional to g. If gravity is stronger somewhere else, then all of that air that's above you is getting pushed down with a greater force on your shoulders, and so you're feeling more of that pressure. The last thing, which is kind of like the key variable for this diagram, is depth, and that's h. Pressure is proportional to depth. Now, for depth, we actually measure down, and we typically always use positive numbers. So what that means is that A and B, because they're in the same fluid, on the same planet, and at the same depth, points A and B are receiving the same amount of pressure from that fluid. Point C, because it is below points A and B, is receiving the greatest amount of pressure because it is at a greater depth. Okay, so the last part of this is that there are different kinds of pressure that you might have heard of. There's absolute pressure and there's gauge pressure. Absolute pressure, just like absolute zero and the Kelvin temperature scale, is based on a true value of zero. So absolute pressure is measured relative to a vacuum. Now, a vacuum is an empty space, and so if there are no particles in a vacuum, that is a pressure of zero. So the absolute pressure of a vacuum is zero, and then the absolute pressure is always measured relative to that. This is a pressure that accounts for atmospheric pressure. So that pressure is going to be large because it's going to have atmospheric pressure added to it to give that actual pressure. Now, when you measure pressure with a tire pressure gauge or something else, you're not measuring absolute pressure. You're measuring what's called gauge pressure. That is the pressure relative to atmospheric pressure. So your tires are inflated on your car from anywhere probably 30 to 35 or 36 psi, but atmospheric pressure is 14.7 psi. So that gauge pressure is, let's say, 30 psi above 14.7. So the absolute pressure of your tires is on the order of 45 psi. So this doesn't account for atmospheric pressure, and so these tend to be smaller, and think of them as local pressures. The relevant equation that's in your equation sheet is P equals P naught plus rho G H. And so that has all of our important variables there. Now I'm going to go back and redefine this. In this equation, gauge pressure is equal to rho G H. That's the local pressure wherever an object is in a fluid, and this P naught is atmospheric pressure. So there's two ways to read this equation. One of them is where P is the absolute pressure. And that means that P naught is atmospheric pressure. So that's one of the ways in which you can use this equation is using P and P naught as absolute and atmospheric pressure, respectively. However, if you're just looking at something like this, where you have 2 or 3 points within a fluid, you don't have to involve total pressure. So P can be pressure at a lower depth, and P naught can be pressure at a higher depth. so more shallow depth. And so you can do this relative to the atmosphere, and you can also do this relative to another point within your system. I'm going to show you what that means. The pressure at point A, if I'm going to use this equation, well, there's the atmospheric pressure, and then there's also the pressure due to its depth. So the pressure at point A is equal to the atmospheric pressure plus the density of the fluid it's in times G, and then based on this diagram, times little h. So that is a representation of the absolute pressure of point A. Because A and B are at the same point, they are equal to one another. So no extra math to do. It's point C that gives us like the peek into the two different ways you can use this equation. If I wanted to do it as absolute pressure, I would say that the pressure at point C is equal to the atmospheric pressure plus the pressure due to the depth within the fluid. Now that's a height of, or depth of big H. So the atmospheric pressure plus rho G big H. So both of these expressions are absolute pressure that account for atmospheric pressure. Now I can also use this to indicate like relative pressure. So if I wanted to do that, I could say, well, the pressure at point C is equal to the pressure at point A plus the pressure due to the depth below point A. So point A is this far underneath the surface. Point C is this far underneath the surface. The depth of point C relative to point A would be the difference between these values. So I could say rho times G times the quantity big H minus little h. So this equation can be like a little tricky to use at the beginning, but once you get used to it, it's pretty easy. And that's it for this section. Next video is on just practice problems.